This is EE300 Linear Circuit Analysis 2, Module 3, Video 5, Vector Interpretation of Frequency Response. As usual, we'll have a review, and then we'll introduce the idea of the vector interpretation of the frequency response. There'll be a first-order circuit example and a second-order circuit example using the underdamped resonant circuit, and then a summary of what we've done. So, review. Okay, we have the idea of the frequency response of the circuit, which is the transfer function evaluated at S equals j omega. And it has two parts, the frequency response magnitude, or the gain of the circuit, and the frequency response angle, or the phase angle, or the phase of the circuit. And those vary as functions of frequency. And we usually plot those, each of those separately, the magnitude and the angle versus omega. We've also seen that you can also plot 20 log base 10, the magnitude of h of j omega, and the angle versus omega on a log scale and get a Bode plot. So we also saw, though, that you could look at the details of first-order, second-order circuits and look at the input impedance, which determined the current in response to a voltage input. And the current would flow in different ways depending on the frequency because of the way the impedance of the individual elements changed. And then you would take that current and multiply it by the impedance of the individual element to get the output voltage for that element. And we saw how the combination of those two, current gets small when the frequency is small, and current gets big when the frequency is big, and so could determine the output of the circuit. And so here's the two examples we've been looking at. The left is a first order circuit with a pole at minus alpha. That'd be minus 1 over RC for the usual RC circuit with the output across the capacitor. We saw that at the frequency omega equals alpha, it has a gain of 0.707, 1 over root 2, and then it rolls off like 1 over omega for increasing omega. At that frequency omega equals alpha, where the gain is 1 over root 2, you can see that the angle is minus 45 degrees, and then it becomes more negative angle, increasing towards minus 90, or decreasing if you want to say it that way, towards minus 90 degrees for highest frequencies. The illustration on the right is the second order underdamped circuit with various values of the damping factor, zeta. So you can see as you decrease the damping factor, you get a peakier and peakier behavior. And so we saw that this had the property that on both sides of the resonant frequency omega 0, at sort of omega 0 minus damping factor, omega 0 plus damping factor, the gain was 0.707 there also. And at those points, you can see in the angle curve, the angle starts out going from plus 90 degrees at at the omega, natural frequency minus zeta omega naught. It goes to an angle of 45 degrees. At the natural frequency, or the resonant frequency, it goes through an angle of 0. And then again at omega 0 plus zeta omega naught, it goes through the angle of minus 45 degrees. And then it tends to minus 90 degrees for high frequencies. And we work that through both in the circuit way and also just by plugging j omega in for S. So the vector interpretation of frequency response. Here's two different circuits. Our original first order circuit, the RC circuit with the output across the capacitor. Here's the RL circuit with the output across the resistor. They both have the same transfer function, and yet they do it for different physical reasons. And if they have the same transfer function, they're going to have the same frequency response. So even though we can explain the frequency response in terms of the physical behavior of the circuit to applied voltages of different frequencies and the resulting currents and how those all interact, you can get the same behavior from different circuits for different reasons. So maybe there's something to the frequency response that really doesn't have to do with the underlying circuit behavior and has more to do with the location of the poles and zeros, since these have the same poles and they have the same system function, transfer function, and they have the same frequency response. So how do we get there? We start by writing the transfer function in factored form. So we pull out scale factor k and then have our n poles as s minus pole location 1. So in our case, the pole has been at minus alpha, so you'd have s plus alpha, all the way up to s minus pole location n. And then we have m zeros, again, z1 to zm. And so if we take the magnitude and the angle of those terms, the magnitude of h of s is just going to be the magnitude of that scale factor k, and then the product of the magnitudes of the factors with the zeros in it divided by the product of the magnitudes with the poles in them, the terms with the poles in them. And the angles are going to be the angle of that number k, and that's going to be plus or minus. It's going to be 0 or 180 degrees or minus 180 degrees. You can't tell the difference between plus 180 and minus 180. And the angle of the sum of the angles of the zero terms minus the angles of the pole terms. So if we could figure out what each one of these terms looks like, and they're the same whether it's a zero or a pole, then we can figure out something about the frequency response. So here's our S-plane, and the number S and the number S0 are just points in that plane. So there they are. And instead of we can interpret those as vectors. So we have a vector from the origin to S and a vector from the origin to S0. And so S minus S0 is going to be a directed vector from S0 to S, right? Because that's the difference. You would have to add S0 to S minus S0 to get S. So there's the red vector there going from S0 to S is S minus S0. Well, the magnitude of S minus S0 then is just the length of that vector. And the angle is just the angle of S minus S0 is going to be the angle that vector makes with a horizontal line. So we can use geometry to figure out what the magnitudes and angles are of the terms S minus S0 when we go to do our frequency response. So let's go back and put j omega in where S was. And so now we have those same expressions, magnitude of k, magnitude of zero terms, magnitude of pole terms, etc., angle k, angle of zero terms, angle of pole. But now we're going from the point, the frequency of interest is S equals j omega. So each of those lines is a vector. Each of those j omega minus something is a vector from the polar zero location to the j omega axis. And so the magnitude of the frequency response is the product of that factor k times the product of the lengths of the vectors from the zeros from the zeros to j omega divided by the product of the length of the vectors from the poles to j omega. And the angle of h of j omega is going to be the sum of that angle k, which is again going to be 0 or plus or minus 180, plus the sum of the angles from the zeros to j omega, to j omega, less the sum of the angles from the poles to j omega. All right, let's look at a concrete example of this with the first order circuit. And it doesn't matter whether we're talking about the RC circuit with the output across the capacitor or the RL circuit with the output across the resistor, they have the same transfer function, alpha over S plus alpha. So when we think about that as h of j omega and want to do this vector business, we pull out the scale factor. We pull out the alpha in the numerator as a scale factor alpha. So there's really only one vector here. That's the vector from the pole at minus alpha to the number j omega, which is going to be up and down the j omega axis for zero, increasing from 0 up to omega's high frequencies. So again, we've already identified the scale factor. It's got a magnitude, which is alpha, and an angle, which is 0. Now for low frequencies, we're talking omega very much less than the corner frequency alpha. So here we are down near the origin, down near j omega equals 0. And when we draw our vector from the pole at minus alpha to the number j omega, which is just a little bit bigger than 0 there, shown for that. The length of that line for small omega, small meaning very much less than alpha, is about alpha. I mean, it's alpha plus a little bit, but not much. So, and it doesn't change much with omega in that region. It's going to be fairly constant, until it starts to get to bigger and bigger numbers. So very small omega values of omega, j omega minus alpha, the length of that is alpha. So the magnitude of the frequency response there is going to be alpha over alpha, the alpha from the scale factor, alpha from the length of the vector from minus alpha to j omega, and that's going to be 1. The angle that vector from minus alpha to j omega makes is small. If it's small enough, you can treat it as 0, but we know that the inverse tangent can be approximated by its argument. So for small angles, the angle there is going to be omega over alpha. That's just remember, you're going to take the inverse tangent of omega, the imaginary part over the real part, so it'd be omega over alpha. And so the angle of h of j omega is going to be 0, the angle of the scale factor, minus omega over alpha. And when you express that as, since omega is in radians per second, alpha is in per second, to get that into degrees, you'd have to multiply it by 180 and divide by pi. So, but what it's really saying is the angle ought to be a straight line coming out for omega equals 0. And it ought to start, it's negative, and it starts at small value, omega equals 0, and it's got a negative slope, and it becomes more negative with increasing omega. That's what that says. So as we increase this, and I wish I had a cool animation for you just to show the point sliding up the j-axis to greater values, but when we get to the value where the frequency is the corner frequency, omega equals alpha, then our vector from minus alpha to j omega has a length of root 2 alpha. So the magnitude of that term is root 2 alpha, and the magnitude of the frequency response then is the magnitude of the scale factor divided by the magnitude of the vector length, divided by the vector length. And so that's 1 over root 2, because it's alpha over root 2 alpha. And then the angle of that vector makes with the horizontal line is 45 degrees. So the angle of the frequency response is 0, the angle of the scale factor, minus the angle from the pole, which is 45 degrees. So we get minus 45 degrees. We go to real high frequencies. We're way out on the j-axis, so you can see that the scale of the pole 0 diagram has changed. We're up there on the j-axis, and so the length of that vector, again, it's actually a little bit bigger than omega, but the length of that vector is approximately omega. So the magnitude of the frequency response, you have the scale factor alpha divided by omega. It rolls off like 1 over omega. The frequency response should get smaller and smaller. The frequency response gain should get smaller as omega gets bigger, like 1 over omega. And again, for large omega, that angle is going to be about 90 degrees, and it's not going to change very much. It's not quite 90 degrees, and it takes it a while to get to almost 90 degrees, but it is still approximately 90 degrees, and so the angle of the frequency response is going to be minus 90 degrees. So this is pretty useful. You can take the magnitude, the length of the vector, and you can see on the left are 3 different examples, very small values of omega, omega equals alpha, and omega very, very big. And you can see each of the vectors from the pole at minus alpha to the value of frequency. And you can see on the plots on the right sort of representative regimes of that, sort of what's the small frequency regime, what's the sort of around j alpha, omega equals alpha regime, and then what's a sort of omega very much bigger than alpha where it starts to act like 1 over omega. And again, you know from the Bode plot that it's actually going to take a while for the angle there at a frequency 10 times alpha is still 6 degrees away from getting to minus 90. And it takes us multiple decades to get there kind of approach. And we'll come back to that in the next video when we talk about Bode plots. Let's see how this looks for a second order circuit. Let's take our underdamped second order circuit. Might come from an RLC circuit with a small value of R, a series RLC with the output across the resistor and a small value of R. So we're gonna write the transfer function as 2 zeta omega naught s. So previously you may have had alpha there, so 2 alpha s over s squared plus 2 alpha s, and again alpha is zeta omega naught. That's just the real part of the pole location. Minus the negative of that would be the real part of the pole location, plus the natural frequency squared. So when we plug in j omega and write the denominator, write everything in factored form on the right, 2 zeta omega naught there is the scale factor. We have a vector from the pole at 0 to the frequency j omega. And then we have the 2 pole terms, one pole at minus zeta omega naught plus j omega naught, and one pole at minus zeta omega naught minus j omega naught. That's an approximation for where the poles are, right? The poles would be at minus zeta omega naught plus j omega naught square root of 1 minus zeta square plus minus square root of 1 minus zeta square, right? Because that's the correction factor. But when zeta is really small, then the imaginary part of the pole location is approximately j omega naught, and we can make this a good approximation. So we've got our scale factor, 2 zeta omega naught pulled out. And now for low frequencies, we're going to be down near the 0. Omega is going to be very much less than omega 0. So we're going to be on the j-axis near the frequency omega equals 0. And the length of the vector from the origin, where the 0 is, to the point j omega is just going to be omega. The vector from the pole at minus zeta omega naught plus j omega naught is going to have a length that's approximately omega naught. Again, it's not exactly. It's got, if you do Pythagoras, you would have to get some value there that's greater than omega naught. But it's approximately omega naught, and the length from the negative imaginary part pole is the same. It's about omega naught. So we can put these together to figure out the magnitude of the frequency response for low frequencies. it's going to be the scale factor 2 zeta omega naught times omega, the length of the vector from the 0 to j omega, divided by the product of the lengths of the vectors from the poles, and each of those is omega 0. So you end up with a net omega 0 in the denominator. Pull out the 2 zeta, that's just a slope. Actually, 2 zeta over omega naught is the slope, but if we normalize the frequency, so we're talking about omega over omega naught, then you ought to get a straight line proportional to omega over omega naught with a slope of 2 zeta. So when we're in the low frequency regime, the vector from the 0 is controlling everything. As omega gets bigger, that vector is going to change, but the vectors from the poles aren't going to change that much. So the omega is the dominant factor there in the low frequency regime. Let's go to the other end of the picture, go to very high frequencies. Excuse me, I need to do the angle first. So for the angles here, again, we have the vector from 0 to j omega, and that's got an angle of plus 90 degrees. And the vector from the pole with the positive imaginary part is about minus 90 degrees, the angle with the horizontal axis there. And the one from the negative imaginary pole has an angle of plus 90 degrees. So when we go to do the angle as the angle of the scale factor, which is 0, plus the angle of the 0, which is 90 degrees, minus the angle, it really should be minus 90 there, which is the angle from the positive imaginary part pole. So there's another plus 90 degrees. And then the angle minus the angle from the negative imaginary part pole, which is minus 90 degrees, plus it's minus 90 degrees. You end up with a net 90 degrees from all those angles. So now let's go to the other side of the big picture, big frequencies, high frequencies. And you can see that we're so far out on the j-axis looking back on this that the 0 and the poles are all look like they're down there at the origin all on top of each other. So it might not be unintuitive to think that when we get this done, it's all going to act like a single pole near the origin. That is, it's going to roll off like 1 over omega, and it's going to have an angle of minus 90 degrees. But let's see how we get there. Let's start with the magnitude. So the vector from here's omega, way out from the 0. And so the vector from the 0 at s equals 0 to the frequency j omega has the length omega. It always has a length omega. But now the vector from the pole at minus zeta omega naught plus j omega naught also has a length that's about omega, because we're so far away from it, way up the j-axis. And even though the other pole was mirror image on the other side of the s equals sigma, the real imaginary part equals 0 line, we're still about omega 0 away from that one, or omega away from that one. Omega is so much bigger than omega 0 here that they're all omega away. So when we go to do the magnitude, we've got our scale factor 2 zeta omega naught. We've got our length of our vector from our 0, which is omega, times over the product of the lengths of the vectors from the poles, also which are omega. So we get 2 zeta omega 0 over omega. That is, the normalized frequency, it rolls off like 1 over the frequency, like we thought it should. Let's look at the angles here. The angle to the line from 0 to j omega is 90 degrees always. But now we're so far out that the angle of the vector from the pole with the positive imaginary part is also 90 degrees. The angle of the vector from the pole with negative imaginary part is 90 degrees. And so the whole angle is 90 degrees, minus another 90 degrees, and you get minus 90 degrees. And that's what we said we thought we should get. If you look at the pole and 0 and pole all sort of on top of each other and think, well, it's almost a pole at the origin. So now let's see what happens near the resonant frequency of omega 0. So here's our zoomed back in now. So we see the 0 at s equals 0 and the poles at minus zeta omega naught plus minus j omega naught. So let's start minus zeta omega naught below the resonant frequency. So omega is omega naught minus zeta omega naught. And we're going to zoom in here. It's the same picture, just zoomed in to look around the resonant frequency omega 0. So we've still got our vector coming up from 0. We've still got our vector coming up from minus zeta omega naught minus j omega naught. And we've still got our vector from our pole with the positive imaginary part. So we can see those three vectors on here. They're just, you can see now that the length of the vector from the 0 at s equals 0 is still going to be omega, but omega is now omega naught minus zeta omega naught. And again, for small enough zeta, that's going to be approximately omega naught. The vector from the pole with positive imaginary part, though, since our frequency is omega naught minus zeta omega naught, has a length which is root 2 zeta omega naught. That is, you can see the triangle, you can see the 45, 45, 90 triangle there. So the vector from the pole to omega, which is omega naught minus zeta omega naught, has equal sides, or equal real and imaginary parts, and so the length of that vector is 2 zeta omega naught. The length of the vector from the negative imaginary part pole is just basically twice omega 0, because we're up near omega 0, and it's coming from down below near minus j omega 0, so that length is about 2 omega 0. So when we go to do the magnitude, we got the scale factor, 2 zeta omega naught, times omega 0, the length of the vector from the 0, divided by the product of the length of the vectors from the poles. One of those is root 2 zeta omega naught, one of them is 2 omega naught. And when you cancel out all the omega naughts and cancel out the zetas, you get 1 over root 2. The angle at that frequency, the same frequency, the angle from the 0, of the vector from the 0 is 90 degrees. The angle of the vector from the pole with the positive imaginary part is minus 45 degrees. And the angle of the vector from the pole with the negative imaginary part is plus 90 degrees, because again, it's coming up from near the j-axis below with a negative imaginary part. And so when you add those up, you get 90 degrees from the 0 minus 45 degrees from the positive imaginary frequency pole, positive imaginary part pole, and then minus 90 degrees from the negative imaginary part pole, and you get a net plus 45 degrees. And let's increase the frequency all the way up to omega 0, and now you can see that the length of the vectors from the 0 and from the pole with a negative imaginary part didn't change that much, but the length of the vector of the pole from the pole with the positive imaginary part changed from root 2 zeta omega naught to just zeta omega naught. So the length of the vector from the 0 remains omega naught, but now the length of the vector from the pole with positive imaginary part is zeta omega naught, and the length of the vector from the pole with negative imaginary part remains 2 omega naught. So when you put those in, scale factor, length of vector from 0, divided by product of length of vectors from poles, you get 1. And I think you can, the angle here, as you can see, the angle from the 0 of the vector from the 0 is still 90 degrees. The angle of the vector from the positive imaginary part pole is now 0 degrees. And the angle of the vector from the negative imaginary part pole remains at 90 degrees. So we end up with a net angle of 0 degrees. Now, as we increase to the other side and go to omega naught plus zeta omega naught, what's going to change? The only thing that's going to change in a big way is the length of the vector from the pole with positive imaginary part. So the length of the vector from the 0 is still about omega naught. The length of the vector from the pole with positive imaginary part is back to being root 2 zeta omega naught. The length of the vector of the pole from negative imaginary part is 2 omega naught still, and so the magnitude turns out to be 1 over root 2. The angle of the angle of the vector from the 0 is 90 degrees. Angle of the vector from the positive imaginary part pole, 45 degrees now, and the angle of the vector from the negative imaginary part pole remains at 90 degrees. And so the total angle there adds up to minus 45 degrees. So when we put these all together and plot the frequency response on the right, you can see the magnitude of the frequency response increasing linearly for low frequencies. That's when we're controlled. We're down here on the j-axis and near the 0. The length of the vectors from the poles doesn't change very much, but this one changes a lot, and that gives us this straight line increasing approach there. We start with an angle that's about 90 degrees, and it's not changing very much because, again, the angles aren't changing very much until we get up closer to one of the poles, which is when we get up into this range here. And when we get up into that range here, the length of the vector from the pole starts to change. And as the length of, instead of being approximated as omega naught constantly. Now you have to worry about it. And as you get up here to exactly when it's minus zeta omega naught below omega naught, then the length of that vector is root 2 zeta omega naught. And that's when we get into this one. You can see the 1 over root 2 factor at, this is sum for zeta is 0.1. So zeta, omega naught minus zeta omega naught, here we are at 0.9. It's a scaled, you can think of it having an omega naught of 1, or you can think of it having a scaled omega naught. As you keep moving by there, the gain gets bigger and bigger until you get to this vector from the positive imaginary part pole gets to be as small as it is. And since that length shows up in the denominator, that makes the gain as big as it's going to get. And then as that vector starts to get big again, the gain starts to go down. And now, at a certain point, you have the three vectors, as we saw, all ending up being the same length omega. And since one of those, the vector from the 0 counts in the numerator and the other two count in the denominator, it rolls off like 1 over omega. You can also see the angle curves for low frequencies, the angle from the pole with positive imaginary part and the angle from the pole with negative imaginary part cancel each other out, basically. So you just get the 90 degrees of the angle from the 0 at s equals 0. When you get into the regime around the natural resonant frequency, then the angle change in the vector from the dominant pole, the pole closest to omega naught, is what's changing things. So as that changes from minus 45 degrees to plus 45 degrees, the angle changes from plus 45 degrees to minus 45 degrees. And then as you get into really big frequencies where all three vectors have angle of 90 degrees, you get a net angle of 90 degrees, minus 90 degrees. Because you got 2 in the denominator and 1 in the numerator. So let's summarize this. It's the poles and zeros determine the shape of the frequency response, and you can figure out what that is using the length of the vectors from the poles or zeros to the j omega axis. When you have a real axis pole at minus alpha or at minus zeta omega naught, that's a corner frequency. This is actually where I did a text substitution of alpha to zeta omega naught. So that should really say minus alpha. And then you have a corner frequency at omega equals alpha, and the gain's down there by 1 over root 2. That's the first order case. When you have a 0 at the origin, then for omega equals 0, you get no DC gain because there's no 0 says you can't have any gain at that frequency. The magnitude is proportional to the frequency for low frequencies. When you get near the j-axis at minus zeta omega naught plus j omega naught, you get the resonant peak at omega naught, omega equals omega naught. And on each side of that resonant frequency of omega equals omega naught, when you change the frequency by zeta omega naught, the gain changes by a factor of 1 over root 2. That makes the half power bandwidth 2 zeta omega naught. So that minus zeta omega naught and that plus zeta omega naught determine the range. When you're within that omega between omega 0 plus minus omega zeta omega naught, the gain is going to be bigger than 1 over root 2, and the power is going to be bigger than 1/2. So the poles near the j-axis, the poles near the frequency of interest, are the things that matter here. And they determine the shape as you go around those frequencies. And the more distant poles and zeros have less influence. They sometimes set up the overall picture, like, you've got 90 degrees here and minus 90 degrees there, and that's sort of an overall arching factor. But it's the one you're driving by, so to speak, that sort of determines what happens. And that lets us sort things out into the effect of this pole, this zero, that pole, etc. For instance, in everything in that second order circuit we looked at, the second order frequency response we looked at, the negative imaginary part pole sort of had a constant influence over the whole thing because we were always far enough away from it that sometimes its length was omega, sometimes length was 2 omega naught, sometimes length was omega 0, but it always had an angle of 90 degrees, and it really didn't do anything to change the shape of things until you got into that high frequency regime where all the vectors were omega long. So it's the poles or zeros near or on, in the case of zeros, the j-axis. They're going to dominate the shape of the frequency response. And we'll explore that in the problems in class and on homework. So what we're going to do next is Bode's method, which is a way of plotting the frequency response as a Bode plot by hand. And then we'll look at how the frequency response and the step response interact with each other and how that influences our design trade-offs. So this has been Module 3, Video 5, Vector Interpretation of Frequency Response, EE300 Linear Circuit Analysis 2.